Hello and welcome to my video about diffraction and wave interference. So diffraction is basically the longer the wavelength, the larger the diffraction. Therefore, also the smaller the frequency, the larger the diffraction. And this is due to the last video that we watched. Frequency and wavelength are inversely proportional because the wave velocity will remain the same. Okay, so here we have a situation where we have a source and we have a slit here, one single slit. So the source creates waves. You can imagine like water waves. And so this would make full rings, right, going all the way around, but you might not be able to continue that forever because of the words and whatever. Okay, so hopefully you can get the kind of the sense of this scale here. It's creating waves like ripples in the ocean or in a lake or whatever. Okay, when the wave hits this point, okay, this hole, or this is like a piece of plywood, it's in the way, it's rock solid. This is not going to move, right? And this is not going to move. When it hits that point, you can see that there's a hole. So it will cause waves to go through the hole as well. And so these waves, depending on their wavelength or their frequency, will have something called diffraction. And so basically they're going to spread out like this. And actually that end wall didn't really need to happen. But you can see here that this, actually I'm going to use red for this. You can see here that the wave has bent around the corner. That's what diffraction really is. It's the bending of a wave around a corner. Okay, so I mean this is not a perfect drawing, but this angle here will get smaller. Okay. The longer the wavelength, the larger the diffraction. So that means it'll bend more. This is basically bending around a corner. Okay, that's basically what's happening here. Okay, so good to see that. Let's take a look at, that's diffraction. That's kind of one of the basic ideas here. Now we're going to take a look at constructive and destructive interference. Now, this is kind of hard to show passively, but I'm going to also show another YouTube video within this YouTube video that shows this very well, and I'm going to give credit to them, Zex Lab Animation. We'll show that in a bit. But before we get to that, and I'll link this video down below as well. The constructive interference pattern would look like this. So basically, if we have a wave, actually let's make it less big. Okay, if we have a wave that looks like this, okay, if we're constructively interfering, then what we're doing is we're putting another wave kind of on top of this wave. And so when those waves are on top of each other, they're constructively interfering with each other. So what happens is that they basically, wherever there's a maximum like this point, that maximum gets doubled because there's both a blue and a red value. So again, maximum and minimum get doubled. So if we can roughly double them, we would be at kind of roughly this point. So we're going to have a bigger max, a smaller min, a bigger max, a smaller minimum, a bigger max. Well, I'm not doing a fantastic job, but I think it kind of shows roughly what's going on, right? They constructively interfered, and so they increased the maximum and increased the minimum. Max and min. Okay, so then we look at destructive interference. Destructive interference is kind of similar, so we're going to start with this red wave. Wow, that's not very good. Okay, we start off with that red wave, but instead, and we always add the amplitudes together. Now, the thing is, if one has a positive amplitude and one has a negative amplitude, you can hopefully see that they are going to destructively interfere. So this height is positive, you can think about it as positive, and this height you can think about it as negative, and so they're going to cancel each other. And same thing over here and over here. These are positive, this is negative, and so on and so forth. So this will actually destructively interfere and make a line right down the middle. So they can cancel each other out. Two waves can actually cancel each other out. It's called destructive interference. And this is actually the phenomenon that's being used in your earbuds, headphones, for noise canceling. What they're doing is they're listening with a microphone to see what sound is coming in from the space around you, and then they play the opposite wave of whatever that is. And because they're playing the opposite, they destructively interfere. Okay, so this is the short, and if YouTube doesn't allow me, I will cut this out of the video. But otherwise, if this is cut out, then I will link it below. So you can see here that these two waves are coming together, okay? And when they meet, they're going to add amplitudes. And you can see there for a second that there they passed each other, and when they are passing, they're adding the amplitudes together and doubled in height. Okay, that is constructive interference, and that works for whether it's a positive, like two peaks or two troughs, like we just saw. But this is called destructive interference, and I will try to nail the timing of this. Okay, I got close. Okay, so you can see here that they are, when they pass each other. Oh, I didn't get it. Nope. There you go. Perfect. Nailed it. When they're passing each other, when exactly the opposite positions, they completely flatline the wave. And then they keep going. And so that's destructive interference, because they add to zero. Now, here's what happens when you put two waves together. Two actual waves, big waves. This is called a standing wave. This is what happens on like a guitar string. Okay, and the points of amplitude are called nodes. The points of, zero amplitude are called nodes. The points of maximum amplitude are called antinodes. So if you look at where the white dots are, those are nodes because they're not moving. So look at this white dot, it does not move. It has zero amplitude, it doesn't move at all, right? But if you look at the peaks and the troughs, those move a lot. In fact, they move double what the original waves did. Those are called antinodes, where the lines are. Okay, so yeah, that's the video. I'll put a link down below so you can pause it yourself and do whatever you want. Watch it again. It's a good, quick little video of that. So we're going to take a look now at a situation where there's two sources and what that looks like for your interference pattern. So it'll make a really cool pattern, and I'm going to try my best to replicate that with my drawing here, which is not going to be perfect, but I think you're going to still see the, ooh, there you go. You're going to see the rough idea here of what that looks like. Okay, so there is source 1, and here is source 2. Okay, it's not perfect, but I think you can see that we have this kind of what I've heard some people call the quilt-like pattern. All these points that I'm doing now in purple, these are the peaks of both waves. So these are going to be our antinodes. Okay, where the peaks and troughs meet up, those are going to be our antinodes. And you can see that it's causing this like quilt-like pattern where it's like it's a consistent location. Now, I kind of got bad at drawing over here, so you can see that it's kind of a little bit messed up here. But especially in the top part, it's somewhat clear what's happening, right? Or at the bottom part here, it looks somewhat clear at what's happening. It's causing this quilt-like pattern, and so those are, or actually, well, those could be our nodes or our antinodes, depending on how the wave is being formed, if they're constructively or destructively interfering. But it's going to cause that sort of pattern. Okay, so that's kind of what that looks like with two sources. What about an interference pattern with a double slit experiment? So now you think about the diffraction that we had earlier, right? And now you also think about it with one source. Now, this one source should cause one type of wave to hit, right? So when it hits, they're going to be the same type of wave in terms of the same frequency, the same wavelength, the same diffraction angle, and unfortunately this is getting to be a little bit difficult to show. Okay, I don't know if this is going to be able to show up on here very well. But now, if you can see here, oh, you know what? It's going to work better if I show it at a different location. My slits are just too far apart, so it's looking kind of funny. And my drawing is not perfect, so it's also looking kind of funny because of that. You can see that on the wall, there's going to be these points of nodes and points of antinodes. And those should cause a roughly repeating pattern. So you can see this pattern on the wall. Like if you draw a line straight down anywhere, you'll see it. But if it's just on a wall, you would see it like that. So this is kind of what's happening with the double slit experiment. Now, when this was done, it was done because light was considered to be a particle. And some people are arguing that it's a wave. And so they were trying to figure out if it's a wave or if it's a particle. And basically, the idea is if it's a wave, it'll cause this sort of interference pattern. And if you do this experiment with light with the same frequency, you'll see this interference pattern. Now, it's more complicated than that because light is weird. It acts in a quantum way. So light, when this is done, it will do what we just showed with an interference pattern. But if you watch, like if you shoot one particle, one photon at a time, and you watch the slits themselves to see which slit that one photon of light went through, it will instead act like a particle where it will go perfectly straight towards the wall. And so if you look at this one, then even if you look at one of the two, now that you know the location of where the photon is, you've changed something about it. You've changed the nature of how it behaves. And there are some really good explanations for why this works, but for Physics 20, it's not necessary to know all that. It's just interesting to talk about the light situation when it comes to waves. So interference pattern can look like this sort of thing, or we can talk about it like destructive and constructive interference like this. Diffraction is bending around a corner, and yeah, that's basically everything for this video. So I hope this video helped you understand diffraction and wave interference a little bit better. Good luck!